My name is Moataz Abdulhafez. I'm a PhD student at the NanoProduct Lab at the University of Pittsburgh. I'll be talking to you today about our research titled Direct Laser-Induced Nanocarbon Formation on Flexible Polymers, Tailoring Porous and Fibrous Morphology. First, I would like to acknowledge my co-authors at the NanoProduct Lab, Ms. Golnaz Tomaraei and Professor Mostafa Bedewy. I would also like to thank the NSF and the University of Pittsburgh for funding this work. Laser-induced carbon, which is also known as laser-induced graphene, is an emerging technique that enables directly patterning conductive carbon electrodes by laser carbonizing polyimide sheets. The method is pretty simple, since it can be conducted with commercial CO2 lasers and with commercially available polyimide sheets known as Kapton in ambient air conditions. The resulting carbon has nice properties. It's porous, conductive, and flexible, which makes it an attractive material for flexible electronics applications. All these properties led to a plethora of applications reported in literature, like biosensors, health monitoring sensors, anti-fouling membranes, and artificial throats. Despite increasing research interest, the fundamental mechanisms underlying the formation of LINC morphologies are still largely missing. In this work, we elucidate these fundamentals by exploring how the laser parameters affect the resulting LINC morphologies and subsequently the LINC properties. This will enable us to control the nanoscale morphology, tune the surface chemistry, as well as tailor the properties for different applications. The key to understanding the process is to understand the process energetics. Assuming a Gaussian beam, the energy delivered at a point on the lasing path is dependent on two things: the intensity of the beam, which changes with beam defocus, and how long the beam stays at a point, which is also defocus dependent. Integrating the intensity with dwell time at a point gives us how much energy is delivered at that point, which is known as the fluence. Experimentally estimate the process fluence by estimating the P power and shape and dwell time for our 40-watt CO2 laser and getting the average fluence as a function of power and defocus. To understand the lasing energetics, we observe that when we laser the polyimide at increasing focus levels, we observe different morphologies, which was not shown before in literature. The resulting morphologies range from porous structures to anisotropic cellular structures to the formation of nanofibers at higher values of fluence. To identify the exact fluence values of these transitions, we develop a technique to create spatial fluence gradients along a lased line by tilting the samples and lasing at different powers. This allows us to monitor the evolution of morphology continuously. Again, we notice the same transitions, which appear to be abrupt. We label the first transition from porous to cellular networks as T1 and from cellular to fibers as T2. We also identify the exact fluence values which they occur at. In addition to imaging, we use XPS to understand how the carbonization and heteroatom content like oxygen and nitrogen evolve with increasing fluence. We notice that the carbonization increases with increased fluence, and we also notice a progressive reduction in heteroatom content that correlates with increasing fluence as well. We conduct resistance measurements and correlate them with Raman data and fluence. We notice a strong correlation between morphology, Raman spectra, and resistance. We conclude that the lowest resistance values are at cellular network morphologies. To summarize, we elucidate the fluence dependence of morphology, molecular structure, and electrical conductivity of laser-induced graphene. This enables us to construct a morphology diagram with delineated transitions represented as isofluence contours. This was enabled by the insight that morphological transitions happen at threshold values of laser fluence.